Okay, so this continuation, the second video on the questions that I was having a look at from the Physics for You book. Question 20 says electricity costs 8p. Need a pen that works. Electricity costs 8p for 1 kilowatt hour. 1 kilowatt hour. And so the question says, how much does it cost to run a 60 watt TV for 30 hours? Okay, excuse, I'm sorry for the noise in the background, it's a very noisy school. Okay, so a way of answering the question would be to say, well, that's 60 watts during 30 hours, and 8p is 1 kilowatt hour, so let's find out how many kilowatt hours this is, and then depending on that, we'll multiply that by 8p. Right, so first of all, the hours, instead of 1 hour, that is 30 hours. So actually, this is 30 times more than that in terms of the time, right? So in a way we can say that 8p instead of 1 hour is going to be 30 hours, so 8p times the 30 hours that are there. That's how much more time than that this is, right? But then we're going to have to divide it, because 1 kilowatt is not what we're using 60 watts. 1 kilowatt is same thing as 1000 watts. So what's the ratio here? Well, if we divide 60 watts by 1000, we get 60 times 10 to the minus 3, or 6 times 10 to the minus 2 watts. So really, that is how much smaller this is than a kilowatt. So we can multiply the previous answer that we had by this fraction, and we should get the correct answer. So if we had 6 times 30 for the hours, and then times 6 times 10 to the minus 2 times 8 times 30, that will give us the right answer for this part. So question 20, it comes out to be 14p. So that one way of doing it is the way that I just explained. It's a little bit more. It's a little bit intuitive, but more intuitive way, or more sort of systematic way, would be to say, okay, I'm going to write this in kilowatts, and this in hours, and it's already in hours, so that doesn't need changing very much. But I need to say, well, how many is 60 watts in kilowatts? Well, I divide it by 60 divided by 1000 is how many 60 watts is in kilowatts, right? And that multiplied by 30, which is how many hours is in hours, so that comes out to be the same thing as doing what I did here, right? And that will be the total number of kilowatt hours, and that I need to multiply by 8 to get the answer, right? So I would get the same thing as I had here. I get 6 times 10 to the minus 2 times 30 for the hours, and then the total cost would be equal that answer times 8, and it comes out to be also 14p. Hopefully that makes sense for question 20. The next question that I was asked about was question 24. Question 24 says that a power station generates electricity at 250 megawatts. That is 250 times 10 to the 6 watts. And it also generates the electricity at 400 kilovolts. Then it says the electricity is transmitted to a distant town along cables with a resistance of 5 ohms. So okay, so that electricity, this amount of power is transmitted to these this potential difference and this resistance on the cables. And the question then is asking, what is the current in the power lines? Well, the formula for current relating power and voltage is, well, you should know that P is equal to IV, right? This should be already in your head, that power is equal to the current times the voltage. So current is the same thing as the power divided by the voltage, and that is 250 times 10 to the 6 divided by 400 kilo means to the power of 3 volts. And so we should have a current that works out to be 625 amps. So that's easy enough for the first part. Part B says, what is the power loss in the cables? Okay, and power loss is calculated by in accordance to the resistance. So power is equal to IV, but V is equal to IR. So the whole of IR can be put inside of this V, and you get I times R. So you get this I first, right? You get that I, and then the V you get IR. So you get I times R, which is I squared R. So that's the power loss through the resistor, and that's calculated by squaring the current, which is 625 squared, times the resistance, which is 5 ohms. And we find that if we do that, we should get an answer of 2 million watts, or 2 megawatts, or 2 times 10 to the 6 watts. That's how much power is lost through the resistor. And this reason, this fact that you get I squared R is the reason why when you transmit power, you transmit, so if I want to transmit power, I do it with IV, right? So I can have a high current and a high voltage, or I can have a really high current and a really low voltage, or I can have a really high voltage and a low current, and I can still transmit the same amount of power, right? So for example, a current could be 1000 amps and the voltage could be 10, or I could have the opposite way around. I could have 1000 volts and 10 amps, and the same power would be in both cases. So which one is more efficient for transmitting electricity? Well, it's the one with the lowest current. And why? Because P is proportional to I squared, right? Or IV, but V is proportional to I. So this is I squared R, which means that if you increase the current by 2 times as much, the power loss increases by 4 times as much. And if you increase the current by 3, the power loss increases by 9. So the way that we transmit power is normally with a very small current and a really big voltage. And we get the same amount of power in that way, and we get much smaller losses in that sense. And that we do using transformers. Okay, don't have to look at that now, but it's all useful to know. So that was for question 24. Okay, and the last one that I had to do was question 20. See if I can finish it in this video. Question 26 has 3 parts, so let's try to do it as quickly as possible. It says, the filament of a 230 volt light bulb is 0.72 meters long. So that we're talking about a filament. Filament is just a thin bit of metal. And it says that it has a radius of 6 times 10 to the minus 2 millimeters. And it says that the resistivity of the filament metal, resistivity rho, is equal to 1.2 times 10 to the minus 5 ohm meters. So with all that information, we have a certain voltage that is fixed for the light bulb. We have a certain length of material, we know it's a filament, we have a certain radius, and we have a certain resistivity. With all of that information, they ask us to solve a bunch of questions. So what's the first part? Calculate the resistance of the light bulb. Well, formula for resistance is resistivity times length over area. So that is 1.2 times 10 to the minus 5 times the length, which is 0.72. It's already in meters, so I don't have to change anything. This is already in the right units of meters. And divided by the area. And the radius is 6.6 times 10 to the minus 2. So what's the formula for the area? It's pi times the radius squared. And if we do all of that, for question 26, we get an answer of 760 ohms for the resistance of that particular configuration of material. So this is a property of the material itself, but with that length and that radius and so on and so forth, that is the resistance that you get for that particular wire. So this doesn't change for the material, doesn't matter what you do, but this changes the resistance according to the length and the area of the bit of metal or material that you're looking at. Now it says calculate the power on 230 volt supply. So power is equal to the current times the voltage, but it's also in this case easier to calculate using the formula that I used before, which is I squared R, because we have actually I don't know what I'm talking about, I'm chatting rubbish. We need to first find the current going through the circuit. So let's find the current. The current, if V is equal to IR, then I is equal to V over R, and that is 230 volts divided by the resistance we just calculated over there. So 230 divided by, that's the same thing as 23 divided by 76. And I get my calculator out. That is 23 divided by 76, 0.3 not 3 amps. And so that's for I, and I'm interested in the power, and that is going to be the current that I just calculated, 0.303 blah, blah, times, use the full number here always, times the voltage, which is 230, and that comes out to be, for 26 part B, 70 watts. Okay, the other way of doing it simply here is, well, if I want to get rid of the I, then, you know, I is equal to V over R. So if P is equal to IV, instead of I can write V over R, so then I get that power is equal to V over R times V. And that is the same thing as V squared over R. So you can write the formula for the power in terms of V and R, or you can write it in terms of I and R like that. So you can always get rid of one of the letters by substituting the other. Doesn't really matter, you do it in 2 steps, or you do it with algebra like this. It's all fine. Only have 2 minutes left. See if I can finish part C. C says the filament of the bulb becomes thinner as the bulb is used. What effect will this have on the resistance of the filament? Well, the formula for the resistance is the resistivity, which does not change however thin it is, times the length divided by the area. And they haven't said anything about the change of length, they say it's thinner. So if it's thinner, what happens? The area is smaller. If the area is smaller, the cross-sectional area is smaller, that means that the whole of the fraction is going to get bigger because it's at the bottom. So if the whole fraction gets bigger, means the resistance increases, which agrees with our idea that a thin wire is going to be a higher resistance than a fat wire. So that, hopefully that makes sense. The R increases, and you can use that argument to justify that. And in part 2, it's power output. So how do we find what will be the effect on the power output? And it says that the hint is that the potential difference across the bulb remains at 230 volts. Okay, so that remains, and power is equal to IV. And you know, so V stays the same. So what happens to the current? Well, if the resistance increases, the current is going to go down, right? So if the current goes down, then and V stays the same, then the power is going to also reduce, right? So the R increases, the resistance increases, but the power will reduce because it's a higher resistance, so therefore the current will be smaller, and the potential difference still remains the same, so therefore the power will be less. And I'm out of time, so see you in the next.